In my previous class, I have already discussed the electric field intensity due to a dipole at axial line. Today, we will discuss the electric field intensity due to a dipole at equatorial line, which is also known as broadside-on position. In the figure, consider AB is an electric dipole where O is the center of the dipole, and let P is a point where a test charge is there from O and the distance is R. We have to calculate the electric field intensity due to the charge minus Q as well as due to the charge plus Q. From minus Q towards P, the direction of the electric field intensity is towards PB because minus Q charge is there, it attracts. Similarly, the electric field intensity due to the plus Q charge is towards PC, that is outward from the positive charge, and BO is L, OP is R, so BP, this is a right angle triangle, so BP is R square plus L square square root. Now we have to calculate the electric field intensity E plus due to the plus Q charge and E minus due to the minus Q charge. These are the strength of the electric field produced due to the charge plus Q and minus Q at point P. So now we have to calculate the electric field intensity due to the charge minus Q, which is represented as E minus equal to 1 by 4 pi epsilon naught Q by R square plus L square whole square along PB, because the point charge we have already discussed. Electric field intensity due to a point charge is equal to 1 by 4 pi epsilon naught Q by R square. So here the distance is R square plus L square square root. So this one is R square plus L square square root whole square. Then similarly, the electric field intensity due to the charge plus Q, E plus equal to 1 by 4 pi epsilon naught Q by R square plus L square square root whole square along PC. If we just noticed the magnitude of E plus and E minus are equal, that it will be taken as E plus equal to E minus equal to E, and the angle between this E plus and E minus is 2 theta, because here the angle PBO is theta, as well as PAO is also theta. We know the theorem that exterior angle is the sum of the two interior angles, so it will be 2 theta. So the resultant electric field intensity E square plus E square plus 2E square cos 2 theta, and 2E square plus 2E square cos 2 theta, it will become, taking common 2E square inside bracket 1 plus cos 2 theta, and 2E square from trigonometry, the formula 1 plus cos 2 theta is 2 cos square theta, so it will become, the square root will become 2E cos theta. From the figure we have to put the value of this cos theta. The direction of that resultant electric field intensity is along PE, and we have to put cos theta from the figure. Cos theta is, we know according to Pythagoras theorem, cos theta equal to B by H. So here B is L divided by H means R square plus L square square root. So it will become L by R square plus L square, and total it will become, finally resultant of the field 2QL divided by 4 pi epsilon naught R square plus L square whole to the power 3 by 2 along the direction PE. So it will become this much. But for an ideal dipole, we know that R is very greater than L, so neglecting this L square, the resultant field becomes E equal to P by 4 pi epsilon naught R cube, which is along PE. So this is all about the expression for electric field intensity due to a dipole at equatorial line. Now we come to another topic, that is what happens when an electric dipole is suspended in an uniform electric field. Uniform electric field means the electric field intensity is distributed uniformly everywhere. Here we have taken a dipole AB and it is just inside an uniform electric field. The electric field intensity E is here, that means it is uniformly distributed, and it will make angle theta. This dipole will make angle theta with that uniform electric field intensity, and the length of the dipole is 12. Two forces acting here, in case of minus q, the force is minus QE, and here at the plus q charge the force is plus QE. That means the forces are just equal and opposite, so the resultant force acting on this dipole is 0. If we just we know when two forces are acting along the single line of the action, they constitute, do not acting on the single line of the action, they constitute a couple, and that couple produces the torque. Torque is the turning force, and you have already know in your 11th class that turning force is nothing but the product of either the force into perpendicular distance between them. And here tau you have written by the symbol tau, either force into perpendicular distance. From the figure, just come to back side, in the figure, that AC is the perpendicular distance between the two forces QE and minus QE, and that force will become, and perpendicular distance AC, if from the figure sin theta equal to AC by 12, so that AC equal to how much? AC equal to 12 sin theta. So you have to put that value in the next AC. We have to put that value, so tau equal to QE into 12 sin theta. So it will become 2QL into E sin theta. As we know, the dipole moment is represented as 2QL, so we have to write P here, so it will become PE sin theta. We know AB sin theta equal to A cross B, so it will also represented as tau equal to P cross E, or P cross E we can represent also. If the electric field intensity is unit 1 and theta is 90 degree, sin theta will become 1, so tau will become P, putting this value tau equal to P sin theta, putting the value of P, putting the value of sin theta, and E, we can get tau equal to P. That means tau is the torque and P is the electric dipole moment. So electric dipole moment of an electric dipole is also defined as the torque acting on it when it is placed at right angles to uniform magnetic field, and the torque will be also maximum when it is placed at perpendicular, and if it is placed parallel the torque is 0, because here sin theta, sin 0 value is 0, so the torque will be maximum when it is placed right angles to that. And in the vector form we can also write tau equal to P cross E. Now come to another new factor, that is known as electric flux. Electric flux is nothing but the number of the lines of force passing per unit cross-sectional area. Suppose we have to take a surface here, and the number of the lines of force passing unit cross-sectional area, we can say that electric flux, and mathematically it is just the product of that electric field intensity and the area vector, so E vector dot ds vector, and the according to the direction we have to put that n cap, where n cap so is the unit vector along the direction perpendicular to ds, and phi equal to closed integration of E dot n cap ds, and E dot n cap ds we can write as E ds cos theta, where theta is nothing but the angle between E and n cap. So this using this electric flux, Gauss had developed a formula and a law also. This law states that for any distribution of the charges, the total electric flux linked with a closed surface is equal to 1 by epsilon 0 times the total charge within the surface. Suppose we take a cubical body means closed surface, and the charge inside is taken as Q. Then the total electric flux through that closed surface is defined as 1 by epsilon naught times the total charge within the surface, and we can write phi equal to Q by epsilon naught, or that phi E dot n cap ds closed integration, that is equal to Q by epsilon naught. So this is all about the Gauss law.